If you want to know where magnets come from, you actually have to look at the crust beneath our feet. The Earth itself generates a massive magnetic field. Thousands of years ago, people discovered that this planetary force was trapped inside naturally occurring jagged rocks. They called these stones magnetite, or lodestones, and noticed they could pull pieces of iron right out of the dirt. Today, we don't need to dig up magic rocks to stick a calendar to the fridge. We engineer artificial magnets, casting them into specific shapes like bars, horseshoes, and discs, built exactly for the job we need them to do. We took a geological curiosity and turned it into a manufactured tool that powers our modern world. These manufactured tools generally fall into three categories. First are permanent magnets. As the name suggests, they hold onto their magnetic field indefinitely, making them perfect for everyday tasks like securing a cabinet door or holding papers to a whiteboard. Second, we have temporary magnets. Ordinary iron objects, like a steel paperclip, can temporarily act like magnets, but only while they are trapped inside the magnetic field of a permanent magnet. Once you remove the permanent magnet, the paperclip loses its pulling power. Third are electromagnets. By running electrical currents through coils of wire, we can create a massive magnetic force that can lift a pile of jagged scrap metal and then drop it simply by switching the power off. You see this same technology on a smaller scale every day. Inside an electric school bell, those copper coils use an electrical current to rapidly flick a metal striker against a gong. Whether it is a natural rock or a powered crane, every magnet relies on a specific internal structure to generate this invisible pulling power. To find the answer, we have to look deep inside a piece of ordinary, non-magnetic iron. Inside these materials are millions of microscopic particles called magnetic domains. In normal iron, these tiny magnetic arrows are facing in completely random directions. Because they point every which way, they cancel each other out. The net result is zero overall pulling power. It is like walking into a bedroom where someone has thrown hundreds of books haphazardly across the floor. There is a lot of material there, but absolutely no organization. A piece of metal is only non-magnetic because its internal structure is trapped in a state of chaos. We can actually fix that chaos. We can physically manipulate these internal particles to create order using a technique called the stroking method. If you take a strong permanent magnet and drag it repeatedly in one single direction across a soft iron needle, you start to change the needle's internal structure. The strong external magnet physically pulls those scattered particles, forcing them to rotate and snap into perfect parallel alignment. Now they are all facing the exact same direction. Suddenly, that messy floor covered in scattered books has organized itself into a perfect, neat tower. A magnet is simply a piece of metal where all the tiny internal forces have been forced into perfect cooperation, combining their microscopic power into one unified magnetic field. Because a magnet's power relies entirely on this delicate internal order, it is surprisingly fragile. This fragility leads to demagnetization. If you expose a magnet to extreme heat, you are adding thermal energy. The aligned particles vibrate wildly until they break rank and scramble. You can also cause demagnetization through physical trauma. Striking a magnet with a heavy tool sends shockwaves through the metal, literally knocking the particles out of their neat lines. Even dropping a magnet repeatedly on a hard classroom floor provides enough physical shock to permanently scramble its internal alignment. Introducing physical or thermal chaos destroys the internal teamwork, instantly turning a powerful tool back into a plain, useless piece of metal. The scientific solution to preventing accidental demagnetization is storing magnets properly using keepers. Keepers are small pieces of soft iron placed across the poles of a magnet when it is not in use. You store bar magnets side by side with opposite poles facing each other, using iron keepers to bridge the ends. This creates a safe, closed loop for the magnetic field, keeping the internal particles perfectly aligned and locked in place. Preserving this alignment has been vital to human history. It allows the needle of a compass to align directly with the Earth's magnetic field, guiding ships across oceans for centuries. By understanding the delicate, invisible order inside a magnet, you can protect the internal alignment that powers our navigation and industrial technology.